Hey Chem30s, Manchak here with video number 2 for this week, which is concept D7, covering pH curves and titration curves again. This will be your very last video lesson, and I hope it is going to be short. So, hey, first off, good on you for sticking it through all the way and making it this way. It's not an easy course to get through, but you guys have done it. So excellent, excellent work. I'm going to jump right into the what we need to cover for this concept, and then we'll just refresh your memories on what I want you to do at the end to finish things up and get ready for your practice quiz and your summative quiz. So interpreting pH curves is where we're going to move through now. This is going to be playing around with our Bronsted-Lowry stuff again, but most importantly, I'm going to have you guys looking at these curves that we would get from doing a titration. We can't do a titration right now because we're not face-to-face, and it's not easy for me to show you one of these. But what I will do is provide a link maybe of somebody doing a titration so you can see it as well if you're curious about that. But it's definitely something that you will do in university at some point when you get there. So remember, we're talking about a pH curve now, and we talked about these in Chemistry 20. A pH curve is simply a graph that represents what's happening to a chemical reaction as we move it through a titration. So a titration, remember, in this case is an acid-base titration, where we're going to be either adding acid to base or base to acid. And the whole goal of a titration is try to figure out a concentration of something that we don't know the concentration of. So in this pH curve, what's happening is we're titrating a strong base with a strong acid. And I'll explain to you in a second how that works. I know that I'm titrating an acid into a base because of a couple of things. Okay, if I just had the title, when I hear titrated with, whatever comes after is your titrant. Okay, it's the thing that's being dropped into the thing that came before, which is the sample. Okay, I also know that if I was just given the graph, that this is a strong acid being added to a strong base, because the pH is going from very high to very low, meaning that we're adding acid to it. Okay, last year we talked about bromethymol blue. I just read it in the next thing in my head. Last year we talked about acid-base indicators as a way for us to tell when we reach the point where we've used up all of the sample. And so that's what this diagram was indicating here, is that we've got, I'm just going to get my pointer out here, is that we've got 3 different indicators, and the ones that we would probably choose is this one here, where we're as close to pH 7 as possible. And at pH 7, that's our equivalence point, the point that is halfway up on this sort of vertical section, or almost vertical section of this graph. Yeah, so let's move on to the next slide, and I may come back to this, bounce back to it in a second. So what we're doing is in a pH curve is we're graphing pH versus the volume of the titrant that we've used for this reaction. From the title, we know the chemicals involved. From the shape of the curve, we can determine relative weak or strong nature of the acid or base. From the scale, we can find the equivalence point, and you can get the concentration of the chemical being titrated. Okay. When you put a title on a graph, remember you must give the person reading the graph enough information to understand what's in there. And this is what's important about graphs that we do in all of our science classes, is they have to communicate lots of information. Okay, titration of nitric acid by 0.1 mole per liter sodium hydroxide. That gives us lots of information. We just need to make sure that we keep it scientific and we put enough information in there that somebody knows what's going on. So if I was to go back here and look at this graph, right, it's told me lots of information in the title. It's told me the volume of our sample, the concentration of our sample, and that it's being titrated with a certain volume or certain concentration of hydrochloric acid. We can figure out how much hydrochloric acid we added by looking at the equivalence point. When you graph a strong acid versus a strong base, like the example that we just looked at, the curve has a shape which shows fairly flat sections at the start, and then a very steep, almost vertical line at the equivalence point, and then another flat section or fairly flat section at the bottom. A strong acid with a strong base, and I'm going to take out my highlighter for this one. Strong acid with a strong base is going to produce very close to pH 7 if they are a strong acid and a strong base. Okay. We also may want to look at what's called a buffering region, and I'll explain what that is in a second when we get into this a little bit further. If we are dealing with one chemical being weak and one strong, then our shapes are a little bit different. And so what I'm going to do is show you this graph to sort of illustrate that as I move my picture all the way around here to completely distract you. So first case scenario. Get my pointer out so you guys can see it a little bit better. First case scenario we just talked about is a strong acid, SA, with a strong base, SB. And that is this blue curve that you see here. So we've got a relatively flat buffering region here, then our strong vertical point, and notice the very middle of it has pH of 7. Okay, and then it flattens out into our strong base. And we know this was a strong acid with a strong base. If this was a strong base with a strong acid, it would be reversed. It'd sort of come down like that, if you can see that, okay? If we did a strong acid with a weak base, what we would end up happening here is we would continue along this line normally, but what would end up happening is it would start to curve up in this direction. So our vertical section is sort of here, and we end up with our equivalence point being below pH 7. That means basically that the strong acid is overruling the weak base. And so we end up with a pH that is below 7. If we did a weak acid with a strong base, so here's our weak acid starting here, okay, what we would end up with is an equivalence point that would be up above 7 because the strong base is basically overruling the weak acid. If you do a weak acid with a weak base, you still get an equivalence point of right around 7. Okay, remember that this could be drawn opposite, right? We could have curves that are going sort of this way instead. Okay, that's indicating that your sample is a base and your titrant is an acid. In the case on this graph, your sample is an acid and your titrant is a base. Okay, so this whole section I basically just explained on this graph. I also have a video on acid-base titration curves that does an excellent job of explaining this stuff too, so it might be worth a quick look for you as well. I wanted to talk about polyprotic entities as well because they're going to change the shape of our graph a little bit. So in some reactions where the acid or the base is polyprotic, so it has the ability to gain or lose more than one proton, we get a different curve. Just to reiterate that point for just a second here, things that are polyprotic, a polyprotic acid would be something like, I don't know, H3PO4, okay? It's polyprotic because it's got 3 protons that it can lose. It can lose 3 hydrogens from it. So it can donate a proton once and then again and then again. On the flip side of this then, and by the way, it's going to do something like this, where it's going to donate a proton and it's going to turn then into H2PO4, 1 minus. And then this one can go down and it can also go through, and I'm missing other reactants for these blabberies just to keep things short. And this turns into HPO4, 2 minus, okay? That's polyprotic, and this one could go down and donate 1 more proton to turn into PO4. Speaking of PO4, PO4 is a polyprotic base, okay, meaning that it has the ability to accept more than 1 proton. It can actually accept 3. It can accept 1 to turn back into this, and accept another one to turn back into this, and accept another one to turn back into that. So we have the ability to be polyprotic in many cases, the ability to donate or accept more than 1 proton. Monoprotic acids and bases, like the ones we've seen in the previous graphs, will only have 1 equivalence point on them, okay? But polyprotic have more than 1 equivalence point. And so here's a good example. This is sodium carbonate, carbonate being a polyprotic base, right? It's CO3 2 minus, right? And there's 2 bumps on this graph. Okay, you can see that there is an equivalence point here and an equivalence point here. What I want you guys to be able to do with these graphs is to be able to interpret, oops, I didn't mean to go to laser pointer, be able to interpret a graph and tell me what's around in each section. So we've got sodium carbonate, so the carbonate ion is what's doing the basic entity here, with a strong acid, which is hydrochloric acid. So what do we have present to start with in this first buffering region? This is the buffering region here. And it's a buffering region, by the way, because the pH isn't changing rapidly. It's changing relatively slowly because there's enough of the base around to neutralize the acid. So what's going on here is that we've got carbonate ions, okay, that are reacting with hydronium ions, okay? And that is forming an equilibrium where we're donating a proton from the strongest acid over to the strongest base. And the carbonate ions are becoming hydrogen carbonate ions, and the hydrochloric acid, the hydronium ions, are becoming water. What's going to happen, though, is eventually all of these guys are going to disappear. And what that point is, when we've used up the very last one of the carbonate ions, we've hit our equivalence point. And then we take a little bit of a sharp curve down, and we have a second buffering region right here. And what's going on in this region is we've lost all of our carbonate ions, but we still have lots of hydrogen carbonate left. And because we're titrating, we're still adding more of our strong acid, which is hydronium ions. And that's going to form another equilibrium that's going to produce H2CO3, and it's going to produce water, very poorly drawn water. Okay, and what happens is we're buffering all the way along here because there's hydrogen carbonate still there to react with hydroniums to neutralize. There's the evidence of our neutralization, right? Water. But when this very last molecule or entity, this very last hydrogen carbonate is used up right here at this equivalence point, then our pH drops again rapidly, and all that we have left down here are hydronium ions, because we've added a little too much, and water molecules. Okay, hope that makes sense. Oh, what happened there? Okay, and water molecules. Okay, I want you guys to be able to communicate that to me as we move through, is what's around in this first buffering region, and then what's around in the second buffering region, and then what's around when we're done. Okay, we've used up all of the carbonate, we've used up all of the hydrogen carbonate. There ain't nothing left other than hydronium and water at that point. Does that make sense, I hope, to you guys? That's what's going on. So that's what a polyprotic graph would look like, with those couple of bumps in there along the way. So the last thing I want to talk about, the last thing for Chem 30, is to talk about buffers. And buffers refer to the combination of a weak acid with its conjugate base in the same solution, or a weak base with its conjugate acid, depending on how you want to look at it. When acids and bases are added to a buffer solution, the pH changes very little, so long as the quantity added is much less than the quantities of the conjugate pair entities in the buffer. This is because the acid or base in the conjugate pair is being converted over to the opposite, the conjugate. 762 of your textbook has a great explanation. The other thing that has a great explanation of this is the video that I included as a resource for this week, which is called Buffers, the Acid Rain Slayer. Excellent job explaining what's going on in this case. If too much acid or base is added to the buffer, then what we hit is we hit a buffering capacity, the point at which we don't have enough buffer left over to handle whatever we're adding to it to neutralize it anymore. So what ends up is what used to be a relatively stable pH drops off or shoots up, depending on what we're adding to the situation. So we can illustrate this by looking at something like this. So here is where we're buffering on this pH curve. And the pH is changing by a relatively small amount here. But when we get to this point right here, that is the point where, in this case, we've run out of our acid, in this case, the acetic acid that is acting as our buffer. And the next hydroxide ion that gets added shoots the pH up, way up, past the equivalence point. We don't have any more of our buffer left over. Why do we care about talking about buffers? Well, they're all over the place in our world. We have examples of them all over the place in our body. For example, there's a hydrogen carbonate buffer that we use in our blood to maintain our blood at a relatively stable pH. And so we don't end up having, you know, massive spikes or drops in our pH, and it keeps our blood chemistry relatively constant. The video that I referred to, the buffers, the acid rain slayer video, which is this one right here, they talk about what our rivers do. He's talking about Montana, but interestingly enough, our rivers and lakes in Alberta have limestone base as well, meaning that they are generally basic to start with, and we end up with a buffering that takes place. So even if we have the effects of acid rain, we still can buffer some of those effects away. So, ladies and gentlemen, that is all that I have to teach you for Chemistry 30. It's done, it's out of the way. And for those of you, I don't know if I'll be using these videos in the future, but for those of you that have done this through 2020, where we worked through the bulk of Chem 30 through an online session, you guys have done extremely well, and I'm really proud of what you guys have been able to do so far with this. So well done, keep it up. I'm proud of all of you guys for what you've been able to do. To wrap up the last concepts for the year, don't forget to finish up these LSMs. If you've got time, for sure do the one for D7 on pH curves. Make sure you get worksheets 3 and 4 done. Do the practice quiz as you've always done. Wait for my feedback. I'll get it back to you within 24 hours, unless it's a weekend. And then once you've got my feedback, follow it and then move on to your summative quiz, your very last one of the course. If there's anything you guys need from me, track me down, fire me an email, do something along those lines. But other than that, I hope you guys are staying safe. I hope you're staying healthy. Please stay in touch. If this is the last time that I talk at you, please stay in touch. I'm going to miss you guys. And yeah, we will hopefully talk soon.